Let's talk about the role of angles in crystallography. So first of all, crystallography is the study of the symmetries of patterns in space. And the space we're talking about is a Euclidean space. When we talk about the symmetries of a pattern, we're considering isometries of Euclidean space. And those are basically classified. They could be just a translation, reflection, or a glide reflection. In particular, I've set myself in the condition where we talk about Euclidean 2 space. So what is a glide reflection? It is a reflection over a certain axis plus a translation along that axis. That is a glide reflection. So all of the isometries of Euclidean 2 space are of this type. And today we will in particular study how rotations and translations interact. So let's recall that these transformations can be written as a new coordinate x prime depends on a matrix times the old coordinate x prime plus translation. The translation may depend on the matrix M, just like in a glide reflection. All of the transformations where M is equal to 1 and we have a generic T, these are translations, and they form a subgroup of the crystallographic group, which is the symmetry of a certain pattern in space. And then we can also study the group of matrices M for which there is an MT inside the group. And these form the point group. And this is not necessarily a subgroup because we just studied the matrices M and not the element MT of the group. So we just multiply the matrices. Now it is nevertheless true that the point group acts on the lattice of translations. This is intuitive yet non-trivial. So the rotations, for instance, that occur in the point group should leave the lattice of translations invariant. So this has strong implications. So again, we set ourselves in the two-dimensional case, and with a two-dimensional lattice subgroup of the crystallography group. We will suppose that the first translation goes in a particular direction, which we'll draw here as the horizontal direction. And we'll consider one point O, and then a point to the left of it, which we'll call A, and a point to the right, which we'll call B. Then we have another translation which translates these points in another than the horizontal direction. And now we suppose that there is also a rotation invariance of our pattern. So we can choose the lattice of translations such that one of these points coincides with the origin for our rotations. So suppose O is such a point. Then let's suppose that we rotate A along an angle alpha, and that we rotate B with the inverse rotation, which should also be a symmetry, along the angle minus alpha. Now, because the rotations act on the lattice, and because this distance D is fixed, we have to have a new distance, D prime, such that D prime is equal to M times D. Because D was the elementary length, we need that M is an element of the integers. Now, we can also compute the distance D prime using the angle alpha. We see that the angle alpha, which is here, is also here, and that therefore this horizontal distance is nothing but D, which is the hypotenuse, times the cosine of alpha. And that's just half the distance between A prime and B prime. And then we have this twice to get the full distance D prime. So from these two, we decide that twice cosine alpha should be an integer. And this puts, of course, a strong restriction on the rotations alpha. Indeed, we don't expect a generic rotation to be a symmetry of a lattice, and indeed we get very strong restrictions even on what possible rotations could be symmetries of a lattice. So what are these? Well, 2 cosine alpha could be any integer from -2, -1, 0, 1, 2. If it is -2, then alpha is 180 degrees. If it is -1, it is 120 degrees. If it is 0, it is 90 degrees. If it is 1, well, cosine alpha is 1/2, then we have 60 degrees. And if it is 2, it is just 0, which is no rotation at all. So the order of the rotation, of the rotations that can be symmetries can be order 2, order 3, order 4, or order 6. These are all possible orders of rotations. So these I'll call crystallographic angles then. For all possible crystallographic groups for symmetry patterns in the Euclidean 2 space, we can only have rotations over 180 degrees, 120 degrees, 90 degrees, or 60 degrees as possible rotations that appear in our crystallographic group.